So today we just have to talk a bit about polynomials. There are a few random facts about polynomials that we have to resolve. So let's take a simple case first. Let's say we have x to the fourth and we want to divide by x minus 2. If we want to do something like that, so what we can do is we know by our previous theory that x to the fourth can be written as some quotient multiplied by x minus 2 plus a remainder, and this remainder will be a constant because we know that the remainder always has degree less than the divisor, and the divisor has degree 1, which means the remainder should have degree 0, which means it's a constant. So now we have this polynomial p of x is equal to x to the fourth, which is equal to this. Now let's evaluate at x equal to 2. So if we evaluate at x equal to 2, what we find is p of 2 is equal to 2 raised to the power 4, because if I set x equal to 2, this becomes 2 raised to the power 4. This will become equal to q2 multiplied by 2 minus 2, because x key value is 2, plus the constant r, right? Because r is a constant, please remember that. But 2 minus 2 is 0, and 0 multiplied by q2, this will become 0. So we find out that the remainder is equal to 2 raised to the power 4, which is equal to 16. Okay? Any questions about this? Something that bothers you? So hopefully, all I'm trying to show is that if you divide by a linear polynomial, and if you want to find out what the remainder is, you can just put in the value into the polynomial and the answer that you will get is the remainder. So this is equal to p of 2. Okay? So in general, I'm just trying to define something. We say, this is just a definition, A is a root of the polynomial p of x. What it means is that x minus a divides p, or in other words, what I mean is p of x can be written as some quotient multiplied by x minus a, right? So this is what we mean by a being the root of a polynomial. Okay? So now let's think about slightly, and from here you can actually see p of a is equal to 0, because when you set a equal to 0, when you set x equal to a, you find out that the polynomial evaluated at the root is equal to 0, right? So any questions about this? So I should probably put this here. A is a root of p of x means, I should say here, p of a is equal to 0, and p of a can only be 0. The only way that it can happen is that the remainder should be 0, which means p of x should be written in this form, which means x minus a divides p of x. Okay? So now let's think of a slightly different question, which is if x minus 1 divides p and x minus 2 divides p, then the question is, does the product divide p? And well, you may think the answer is obvious and the answer is yes, but it's not that obvious. Let me give you another example, right? I mean, take an example of, say, let's say we know that 6 divides 12 and 4 divides 12. But note that 24 does not divide 12, right? So you should understand this fact that if one factor, so 6 divides 12, 4 divides 12, but the product, which is 6 times 4, clearly does not divide 12. So here we have a very similar case that x minus 1 divides p, x minus 2 divides p. The question is, does the product divide p? And it turns out the answer is yes, but the reason is slightly involved, not too involved, but you really have to sort of think about what you're doing. And what you're doing is essentially something like this. So let's look at this slowly. So we know that x minus 1 divides p. So if x minus 1 divides p, this means p of x is equal to some quotient q of x into x minus 1. That's what it means that x minus 1 divides p. So what it means is that this by that has to be true. Now I say, and please note, I could write this also as, I could have written this statement, I'll write it out here in a slightly different way. If 1 is a root of p and 2 is a root of p, then this becomes a kind of a weird question to ask, because if 1 is a root of p and 2 is a root of p, then does the product divide p? That's another way to think about the problem. That's another way that you could think about it. But anyway, coming back to this. So now we also know that, x minus, now we have x minus 2 divides p. Well, if x minus 2 divides p, this implies, because 2 is a root, p of 2 is equal to 0. So let's evaluate p of 2, right? So p of 2 will be equal to q of 2 multiplied by 2 minus 1, right? It's just going to be p of 2, I've substituted x equal to 2, p of 2 is equal to q of 2 multiplied by 2 minus 1. But now, and I know this is equal to 0, but q of 2 times this is just equal to q of 2, 2 minus 1 is just 1. So this means q of 2 is equal to 0, right? So q of 2 is equal to 0. So if q of 2 is equal to 0, i.e. we have just found out that q of 2 is equal to 0. So if q of 2 is equal to 0, this implies, this is pretty neat, 2 is a root of q. Also, it's a root of p, but it's also a root of q. So what that means is, i.e. q of x can be written as a product of an other polynomial, q of x equal to x minus 2 multiplied by r of x. So what then, like if you put all of these things together, what we find out is that p of x is equal to q of x, which is equal to x minus 2 multiplied by r of x. Here's r of x, and you also have x minus 1 coming in, because, so let me write it out slowly. So P of x is equal to Q of x into x minus 1, that's this equation, and then but Q of x is equal to x minus 2 into R of x, so I can write it as R of x into x minus 2 into x minus 1. So now you can see that this product divides P of x, and that's the question. So the answer is, we asked this question and the answer is yes, it does. But the argument requires a bit of effort because it's not obvious that if two things divide something, then the product of the two things divide that thing. In fact, there's this very rich theory in algebra in which you're sort of looking at the analogues of, so you can see that this statement is false because these are not prime numbers. But if you had let me try to erase. So I'm going to erase this part of the board. So agar if you look at this, so let's say if you have a number in which I say 2 divides n and 3 divides n and 7 divides n, and so then we can claim that 42 divides n. And the reason why we can do this is because these are distinct prime numbers. These are distinct primes. So you can see that these linear polynomials are playing the role of distinct primes, but what does it mean? So all of that depends on more theory that we are going to consider in school, but I'm just trying to build an analogy here. But I mean, the answer to this question is yes. And in general, if you have n roots, then what you will have is that polynomial can be written as a product of n linear factors along with a residual polynomial. Okay. One other little thing, I'm just trying to tie in some loose ends. So here's another little thing, which is, say a polynomial P of x is a polynomial with degree 5. It can have a maximum of 5 roots. Why can it have a maximum of, it can have a maximum of 5 roots. So why is that? It can have a maximum of 5 roots because let's assume, let's assume it has more than 5 roots. So assume it has, so we're going to prove it by assuming it has more than 5. So let's say it has 6 roots. It has more than 5 roots, say 6. Then P of x can be written as a product of these 6 roots along with a residual polynomial. And now you can see, let's say the residual polynomial R of x is of the form x b x to the L plus something else, where L dot dot dot, where L has to be greater than or equal to 0, right? It would either be a constant or it could be a linear or a quadratic or a cubic polynomial, I don't know what it is, but it at least has, it's at least a non-zero constant, and b is not equal to 0, that we are guaranteed. So then you can see that P of x is of the form b x to the 6 plus l plus lower order terms, and that's a problem because this is also equal to x to the 5, and I could have had a constant here, but it's of the form x to the 5 plus other terms. So this guy cannot be equal to this guy because this is x to the 6 at least. The least value is equal to 6, and this value, the maximum value, is x to the 5, so that these two polynomials cannot be equal because the coefficients of each power have to match, and there is a power of 6 or 7 or 8 here, and there is no corresponding power on the left hand side, which means that hence our assumption was false. Our assumption was false, right? Because we have arrived at a contradiction. This is a contradiction, and our assumption was false. Okay? Just one last thing and then we're going to stop. So this basic idea that if you have a degree n polynomial, the maximum number of roots that it can have is n. And now I'm just going to use that idea in a very simple way. So before I begin, let me ask you a question. Let's say you have a linear polynomial. Let's say p of x is of the form ax plus b. So now note how many times can this be equal to. So remember, at a root the value is 0, right? So there's only one unique value where it can be equal to 0, and you have drawn straight lines. This is a straight line, this is another straight line, this is another straight line, right? I mean, you can only have a unique 0, right? This is the unique spot where it is 0, and here's the unique spot where the function is 0, and here's the unique spot where the function is 0. So the function gets to be 0 at one unique spot in a linear polynomial. Now if it turns out, if you have, if for example p of x, which is a linear polynomial, is equal to 0 at two distinct x's, right? Then the only option is that the polynomial, this implies that a equal to b equal to 0, i.e. p of x is identically equal to the 0 polynomial. Why is that? Because we know a polynomial of degree 1 can have maximum of 1 root. Here we found 2 distinct roots, which means it can't be a degree 1 polynomial, it has to be identically 0, i.e. it has to be this polynomial, a polynomial which takes on exactly 0 values over here. So we can apply something very similar over here, and this is an application of this idea, right? That a degree n polynomial can have a maximum of n roots, and there's an argument here. In fact, you could have used this argument for a problem that you tried to solve earlier in the book. I don't know, this was some kind of question 90 something in which you have to talk about whether if you multiply two polynomials you could get the 0 polynomial. You could get a polynomial of degree less than what you started out with. Now this last thing, which is, let's think about a problem that we dealt with earlier, which was x minus a over x minus b, c minus a, c minus b, plus Now we have x minus c, x minus a over, instead of c, we will be coming back to c ka bajaye b minus c and b minus a plus x minus b and x minus c over b ke bajaye you will get a minus b and b ke bajaye a minus c minus 1 is equal to 0. This is what we want to prove. So maybe this is unclear, but let's look at this. This is what we are trying to prove. Okay? So we are trying to prove that this polynomial is identically equal to 0. Now please note, so this is a polynomial. This is the polynomial p of x. Okay? So I'm not including, so this is the polynomial. So this whole beast minus 1 is the polynomial. Okay? And so we have p of x is equal to 0. That's what we have to prove, that this polynomial from here all the way up to here is a 0 polynomial. Okay? Is this clear? We're talking about this polynomial. Is this equal to 0? That's the question. Well, note p of x is a quadratic polynomial. It's a degree 2 polynomial, right? Why is it a degree 2 polynomial? Because you just have x squared. And the second thing is that we know the roots. X equal to a is a root of this polynomial. Why is it a root? Because when I set x equal to a, this goes to 0, this goes to 0. This becomes a minus b, which cancels this. This becomes a minus c, which cancels this. So it becomes 1 minus 1, which is equal to 0. So x equal to a is a root. And by symmetry, I know if x equal to a is a root, x is equal to b and x is equal to c are roots. Note also, we know a is not equal to b is not equal to c, because otherwise this polynomial would not make sense. For example, if a were equal to b, then you're dividing by 0 and this would be a nonsensical question. So we already know that, right? So we know this. So this means we have found 3 roots. We have 3 roots of a degree 2 polynomial, which is really not possible, right? You can't have 3 roots of a degree 2 polynomial, which implies that p is identically equal to 0, which is exactly what we wanted to prove, that p is identically equal to 0. Because you can't have 3 roots of a degree 2 polynomial exactly for the same reason as you can't have 2 distinct roots of a linear polynomial. Because the maximum number of roots that you can have for a linear polynomial is 1. अगर आपके पास 2 roots मिल रहे हैं, that means that the polynomial has to be 0 और कोई alternative नहीं है आपके पास. Similarly, यहाँ पे चूँकि आपको 3 roots मिले हैं, so what that means is that the polynomial has to be identically equal to 0, because a non-zero degree 2 polynomial can have at best 2 roots and not 3 roots. Now, that's all that I had to talk about today. There is homework for you guys. You never want to be without homework. So let me upload the homework. And the homework is, let me try to upload so let me write down the homework, which is, so this is the homework which is due on Wednesday, and this will be questions 146, 150, 151, 152, 153 and 154. So these are the questions that you need to do, and I think we are done. Great, thank you.